Good morning, students. In continuation to the studies class. So in this class, we are going to show there is an uncountable set of measure 0. Or in the examination, they may ask like, show that construct an uncountable set of measure 0. So for this, say let E naught be the interval 0, 1. You denote the interval 0, 1 by E naught. Now, you divide the interval 0, 1 into 3 equal parts and remove the middle third part the middle third part is, as you know, 1 by 3, 2 by 3, right? So we divide the interval 0, 1 into 3 equal parts and we remove the middle third part, and let E1 be the union of remaining two closed intervals, say 0 comma 1 by 3 union 2 by 3 comma 1. Understand this? So in the first step, we divide the interval 0, 1 into 3 equal parts and we remove the middle third part 1 by 3, 2 by 3, and the remaining two parts we keep it as it is and we take as denote that by E1. Now again divide each of these two subintervals into 3 equal parts and remove the middle third parts. The middle third parts are 1 by 9, 2 by 9 for the year, and 7 by 9, 8 by 9 year. So you remove this and let E2 be the union of remaining 4 intervals, year 2, year 2. So this is E2 is 0, 1 by 9 union 2 by 9, 3 by 9 union. Next is 3 by 9, 7 by 9 and 8 by 9 comma 1. Okay. You continue this way. Continuing this way, we obtain a sequence En. N is equal to 1 to infinity of each one is a union of disjoint closed intervals such that first one is E1 contains E2, contains E3 and so on. In general, En plus 1 is contains En. En plus 1 is contained in En, and En is a union of 2 power of n closed intervals, each of length 1 by 3 raised to n. This you know it. En is the union of 2 power of n closed intervals, each of length 1 by 3 raised to n. Therefore, measure of En is what? Measure of En is, so each of length, this one means 2 by 3 raised to n for each n. Measure of E1 is, so what will happen here? 1 by 3 raised to n plus 1 by 3 raised to n up to 2 power of n times. So it will becomes 2 by 3 power of n for each n. Now you take C to be the intersection of all these sets En. You take C to be the intersection of all these Ens. What will happen? Then this set, the intersection of all these sets En is called the Cantor set. This is the Cantor set. Here clearly each En is measurable. Since each En is closed for each n, the Cantor set C is also measurable because it is the countable intersection of closed sets, means C is measurable. Okay. Now, since each En is a decreasing collection of measurable sets, now En is equal to infinity is a decreasing collection of measurable sets, and measure of E1 is definitely finite because measure of E1 is definitely, this is a E1, so measure of E1 is definitely a finite number. So measure of E1 is finite. Therefore, by the previous results that we have mentioned, measure of intersection n is equal to 1 to infinity En is equal to what? Limit n tends to infinity, measure of En. Measure of intersection n is equal to 1 to infinity En means what? This is C. So measure of C is equal to limit n tends to infinity 2 by 3 raised to n, that will be equal to 0. Because you know that limit n tends to x power of n is 0 if mod x is less than 1. Here mod x means 2 by 3 is less than 1. So now we have constructed a set of measure 0. Now we need to show that this Cantor set C is uncountable. Then we have the required proof like a uncountable set of measure 0. Right? Now we need to show C is uncountable. For this, suppose C is countable, what will happen? Let's see this. Suppose on the contrary, you assume that C to be countable. C is countable means we can list the and let the elements of C be arranged in a sequence as follows. C is equal to C1, C2, etc. and so on, countable collection. Now, since C1 belongs to C, C1 definitely belongs to E1 because C is the intersection of all these ENs, right? C1 belongs to E1, and so if C1 belongs to E1 means E1 is the union of two disjoint intervals, therefore C1 lies in one of the interval. I understand this. So C1 is, say C1 belongs to E1 means E1 is the union of two disjoint intervals. Okay, there is no element common between these two, means C1 lies here or C1 lies here, right? Therefore C1, okay, C1 lies in one of the two disjoint closed intervals in E1. So, and does not lie in the other. Sure, if C1 lies in this interval, say 0 comma 1 by 3, it certainly cannot lies in 2 by 3 comma 1 by n, or if it lies in 2 by 3 comma 1, then definitely it doesn't lies in 0 comma 1 by 3 interval, right? So therefore one of the two disjoint closed intervals in E1 fails to contain the point C1. So denote that by A1. So you denote the interval which does not contain C1 by A1. Similarly, next step is one of the two disjoint closed intervals E2 whose union is A1 fails to contain the point C2. Okay, denote it by A2. You continue like this. Continue this way. We construct a collection of sets n is equal to 1 to infinity, which possess the following three properties. What are the three properties it follows? Say, look here. An is closed because An is one of the intervals. Closed interval means An is definitely closed, and An plus 1 is certainly contained in An plus 1 is certainly contained in An. Okay, and An is, in fact, An is contained in where? Ens, because En is A1. We have the disjoint intervals, so we have denote An by the interval which does not contain Cn, right? So Cn doesn't belongs to An. These are the three conditions. By nested interval theorem, what will happen? Intersection of n is equal to 1 to infinity An cannot be empty. By nested interval theorem, intersection n is equal to 1 to infinity An is not equal to empty. Let x be the element which is in the intersection. Let x belongs to intersection n is equal to 1 to infinity An. Then by property 2, what will happen? So by property 2, intersection of An is contained in intersection of En. Intersection of En is C, means x belongs to intersection of En means x belongs to intersection of En, which is C, means x belongs to C. Now x belongs to C means what will happen? X is equal to, certainly, because the elements of C being arranged like C1, C2, etc. and so on. Therefore x will be look like some Ck. Therefore Ck, that is equal to x, belongs to C, means intersection of An. Intersection of An means intersection of An definitely contained in each of A1, it contains in A1, A2 and so on, because it is the intersection, means it is certainly contained in Ak, means therefore Ck contained in Ak. But by property 2, Ck, by property 3, Ck should not contained in Ak. But here we have a contradiction, like say Ck is contained in Ak, which is a contradiction. Okay, why this contradiction arises? Due to our assumption that C is countable. Therefore C must not be countable, means C must be uncountable. Already we have shown that C is measure of C is 0. So now we show that C is uncountable. Thus the Cantor set C is an uncountable set of measure 0. That's the Cantor set C is an uncountable set of measure 0. Now let us take, you know what is meant by an equivalence relation. Now let us take up the axiom of choice. Axiom of choice says, if A is a collection of disjoint non-empty sets, then there is a set P containing or consisting of exactly one element from each set in A. If A is a collection of disjoint non-empty sets, then there is a set P consisting of exactly one element from each set in A. This is the axiom of choice. So now we are going to prove another important theorem. So this theorem says there is a set that is not measurable, or in other words, construct a non-measurable set. There is a set which is not measurable. We are going to construct this set. Okay. Yes, this is also very interesting. Say let Q1 be the set of all rationals in the interval -1, 1. Q1 be the set of all rationals in the interval -1, 1. How to extract rationals means, so we have to take the intersection of interval -1, 1 with rationals Q, then we get the set of all rationals in the interval -1, Q, that is Q1 is equal to Q intersection -1, 1. Now Q1 is countable. Okay, since now Q1 is countable because this is countable, so intersection is countable. So now since Q1 is countable, its elements can be arranged in a sequence as, okay, so because say Q1 be the set of all rationals in -1, 1 means, so this is rationals are countable, therefore Q1 is countable. So its elements can be arranged in a sequence as Q1 is equal to R1, say R2 and so on. Now define a relation tilde on 0, 1, the interval 0, this is very important. Define a relation tilde on 0, 1 by setting x is any two elements in 0, 1 means x is related to y if y minus x is a rational in Q1. You define a relation tilde in the interval 0, 1 as x is related to y if y minus x is a rational in Q1. Y minus x is a rational in Q1 for every xy belongs to 0, 1. Certainly we can show that this relation tilde is an equivalential relation in 0, 1. It's an equivalence relation in 0, 1, that we have shown it here. So it is equivalence relation means what? It is reflexive, symmetric and transitive, that we have shown it here. Okay. So now equivalence relation means what will happen? So it partitions the set into disjoint equivalence classes. So the special property of equivalence relation is particular property of equivalence relation is it partitions or breaks up the set into disjoint equivalence classes. Okay. So now we denote each of the equivalence classes by E alpha, and you know that the union of all these equivalence classes is the whole set which is 0, 1. So union of all these equivalence classes E alpha is the whole set 0, 1. You call by this number 1. Now these equivalence classes, how they looks? Equivalence class E alpha is, it is generated by the element x alpha. So it contains set of all y belongs to 0, 1, right? Set of all y belongs to 0, 1 such that x alpha is related to y alpha, or set of all y belongs to 0, 1 such that x alpha is related to y alpha means what? Y minus x alpha is contained in Q1 means that is Rn belongs to Q1, or in other words this can be written as y can be written as x alpha plus Rn, set of all x alpha plus Rn, where x alpha plus Rn means y belongs to Q1, y belongs to 0, 1. Set of all x alpha plus Rn, where x alpha plus Rn belongs to 0, 1. Now therefore this belongs to 0, 1 means what? Each E alpha is countable. Each E alpha is countable. Each E alpha is countable because Q1 is countable, and the collection E alpha is uncountable, but the collection E alpha is uncountable since 0, 1 is uncountable. Okay, since 0, 1 is uncountable. Okay, this collection E alpha is uncountable since 0, 1 is uncountable. By axiom of choice, there is a set P. What will happen? By axiom of choice, there is a set P which contains exactly one element from each equivalence class E alpha. There is by axiom of choice, there is a point P which contains exactly one element from each equivalence class E alpha. Put Pn as P plus Rn. Put Pn is equal to P plus Rn, where Rn belongs to Q1. Put Pn as, sets Pn as P plus Rn, where Rn belongs to Q1. Now we show that the collection Pn is pairwise disjoint. We can show that this collection of sets are pairwise disjoint, because if you assume that there is a common point between Pn and Pm means that is y belongs to P intersection of Pn and Pm for n not equal to m, then definitely there exists two disjoint elements x alpha comma x beta belongs to P, such that y can be written as x alpha plus Rn and the same y can be written as x beta plus Rm. This implies x alpha x beta minus x alpha is what? Rn minus Rm. Rn minus Rm, that can be written as say Rk, right? Now x alpha comma x beta belongs to 0 1 and Rk belongs to minus 1 comma 1, and so Rk belongs to Q1. Rk belongs to Q1. Rk belongs to Q1. Therefore, x alpha is related to x alpha. Yes, understand this. Now x alpha comma x beta belongs to 0 1 means therefore Rk belongs to minus 1 comma 1, and so Rk belongs to Q1. Therefore x alpha is related to x beta, which is a contradiction by the definition of P. So P intersection Pn intersection Pm is equal to Mt for n is not equal to m. Hence Pn n is equal to 1 to infinity is a sequence of disjoint sets. They are the sequence of disjoint sets. Now we show that the interval closed interval 0 1 is contained in n is equal to 1 to infinity Pn, which is in fact contained in the interval minus 1 comma 2. You call by the number 2. Now P is certainly contained in 0 1. Now certainly P is contained in 0 1, and P plus Rn certainly contains in minus 1 comma 2, right? For every Rn belongs to Q1. Hence what will happen? Pn belongs to where? Pn belongs to P plus Rn means Pn belongs to minus 1 comma 2 for every Rn belongs to Q1. So therefore union of n is equal to 1 to infinity Pn belongs to minus 1 comma 2. Let x be the element in 0 1 be any arbitrary element. Then by 1 what will happen? X belongs to E alpha for each alpha, because union of E alpha is 0 comma 1. Therefore then by 1 x belongs to E alpha for some alpha. We know that P contains exactly one point or one element from each E alpha. Let x alpha be an element of E alpha which is in P. Since x alpha is also element of E alpha and x is also, by this assumption x also belongs to E alpha. We have x alpha comma x belongs to E alpha means they are in the same equivalence class, means they are related. X alpha is related to x. Now x alpha is related to x means what? By definition x minus x alpha is equal to x minus x alpha belongs to Q. Means x minus x alpha is equal to Rn for some Rn belongs to Q1. This implies x is equal to x alpha plus Rn, where x alpha belongs to P, Rn belongs to Q1. Now x alpha belongs to P, Rn belongs to Q1 implies therefore x belongs to Pn. X belongs to Pn for some n. This implies x belongs to Pn means definitely x lies in the union of n is equal to 1 to infinity Pn. Now we have taken x to be element of Pn, x to be element of 0 1, and we have shown that x is an element of union n is equal to 1 to infinity Pn. Therefore 0 1 is contained in union n is equal to 1 to infinity Pn. Okay. Now we show that P is not measurable. P is not measurable. On the contrary, just suppose that P is measurable. Then what will happen? P is measurable means each Pn is measurable, because P is the union of this means. So then each Pn is equal to Pn is P plus Rn is measurable. Measure of Pn is same as measure of P, because measure of Rn is 0. So on measure of Pn is equal to measure of P, and right, measure of Pn is equal to measure of P, and measure of union n is equal to 1 to infinity Pn is equal to summation n is equal to 1 summation I is equal to 1 to infinity measure of n is equal to 1 to infinity, sorry, it's not I, it is n is equal to 1 to infinity measure of Pn. From 2, what will happen? We have measure of 0, 1 is less than or equal to measure of, the 2 says, what 2 says? Yes, 2 is 0, 1 is contained in union n is equal to 1 to infinity Pn, which is in fact contained in minus 1 comma 2. So here by 2 measure of 0, 1 is less than or equal to measure of union n is equal to 1 to infinity Pn, which is less than or equal to measure of minus 1 comma 2. This implies measure of, this one is the length of the interval, which is 1, which is less than or equal to summation, this is nothing but summation n is equal to 1 to infinity measure of Pn, which is less than or equal to measure of this is 3. So this implies 1 is less than or equal to summation measure of Pn is same as measure of P. So measure of P, measure of P, measure of P infinite times means m of P, measure of P and so on, which is less than or equal to 3. Look here. Now if measure of P is 0, measure of P is 0, then also this case is not valid because 1 is less than or equal to 0 is less than or equal to 3. So it cannot holds true, right? And if assume that measure of P is infinity means, so this also infinite terms means, then also this choice is not possible, means both choices, measure of P is 0 if measure of P is 0, summation measure of infinity if measure of P is greater than 0, both choices are not allowed here. So both choices are not allowed here means, so the assumption that P is measurable must not be true, must not be true. So P must be not, P is not measurable. Okay, understand this? So this is the constructed set P is not measurable. So P is an uncountable set. So P is an, look here, P is an S, we have constructed the set P S which is not measurable. We constructed set P which is not measurable. This is also an important result here. Okay, thank you.